Look down the corridor of a modern AI data center. Thousands of synchronized GPUs operating simultaneously, drawing massive amounts of power to train a single model. Infrastructure operators often assume that scaling accelerator count directly yields higher throughput. The operational reality is different. The true metric of success is model flops utilization, or MFU. It measures the actual mathematical work completed by the system, separating productive calculation from powered-on idle time. AI training relies heavily on synchronized workloads. During an all-reduce operation, thousands of GPUs finish a calculation and simultaneously fire massive bursts of data across the network to coordinate their state. Classical equal-cost multipath routing distributes these flows statically. When synchronized, high-bandwidth elephant flows happen to hash onto the exact same physical links, they collide. Top-of-rack switches buffer these microbursts until their queues fill. To prevent packet loss, they send priority-based flow control pause frames backwards to the source. This congestion backpressure ripples through the fabric, halting entire GPU clusters. Spending millions on accelerators results in significant stranded capacity if the underlying fabric topology is prone to persistent, synchronized congestion stalls. Current data center management relies on siloed logic. Switches route packets, DPUs offload processing tasks, and CM platforms monitor security alerts independently. This creates an operational blind spot. A localized delay in one specific domain cascades invisibly into another, making root cause analysis difficult during live workloads. Take a retrieval augmented generation pipeline. A minor metadata hotspot on a storage controller slows down a vector search. That microsecond delay in retrieval translates directly into a GPU waiting for context, burning expensive idle time. Resolving these cross-layer bottlenecks requires replacing fragmented, layer-specific dashboards with a single multi-layer topology model that links storage, network, optical, and compute state. The primary constraint on AI performance is not just the hardware, but the lack of a cohesive mathematical framework governing the data flow between it. The PTCP AI Factory is an out-of-band decision and evidence headend. It operates as an overlay across the existing infrastructure stack, rather than acting as a direct replacement for switches or storage controllers. This diagram details the base hardware layer. GPU servers, top-of-rack switches, and storage controllers stream localized telemetry. The central control plane ingests this data, normalizing it into a unified geometric graph, mapping edges, trust, capacities, and performance metrics. To identify congestion before queues collapse, the system calculates conditional value at risk, or CVAR. This isolates the rare, highly destructive tail latency events that ruin AI workload timing. Instead of routing by the shortest physical distance, the system calculates a geodesic path. This is the minimum risk route, dynamically selected to avoid forecasted tail latency spikes. While standard routing pushes traffic blindly into congested hash paths, risk-weighted geodesic routing actively steers synchronized AI flows around predicted pressure points. Treating the network as a calculated geometry allows operators to bypass the statistical failures common in classical routing. As AI clusters scale, the physical backbone transitions from copper cabling to high-density optical circuit switches. Optical health metrics, such as bit error rates, queue margin, and insertion loss, dictate fiber signal integrity and must be optimized alongside standard packet routing. This flow diagram illustrates how the control plane treats the physical optical modules and circuit switches as distinct telemetry endpoints within the overarching geometric graph. The architecture schedules bounded physical circuit changes at the optical level, while strictly keeping latency-heavy eBPF software hooks where they belong, on the Linux and DPU fast paths outside the optical signal loops. Structural optimization demands a system fluent in both the software logic of packet queues and the physical reality of fiber connections. This geometric approach extends directly to data center security. Traditional payload inspection fails when advanced persistent threats use encryption, credential abuse, and slow lateral movement to hide in plain sight. The system applies dTopo, a methodology that detects threats mathematically. It identifies anomalies by observing physical deformations in network trust, graph curvature, and cut capacity over time. This map illustrates the risk of traditional response. Blindly quarantining a compromised node like host X can sever critical AI dependencies. Using dTopo, the system stages safe containment edges, precisely isolating the compromised region while maintaining intact connections to adjacent nodes. In a synchronized AI cluster, security must operate as precise topological surgery, avoiding blunt force isolation of healthy resources. Infrastructure engineers correctly distrust opaque black box software agents, making unverified changes to live data centers. The system operates under a strict safe envelope protocol. The default posture is shadow observation, calculating and dry running action plans without executing them. This datasheet preview shows the requirements for live actuation: cryptographic identity binding, blast radius simulation, explicit operator approval, and confirmed rollback readiness. Every executed action generates a procurement-grade evidence pack. This immutable cryptographic trace proves the mathematical rationale for a change before a single packet is rerouted. Enterprise automation is only viable when it provides exact, rollback-guaranteed forensic proof to the human operators responsible for the infrastructure. This rigorous out-of-band architecture yields specific empirical improvements during deterministic self-tests. This chart details ProofPack outcome metrics. The findings highlight a 37.8% reduction in retrieval-augmented generation latency, achieved by staging geodesic actions. On the compute layer, mitigating fabric tail risk produces a 13-point uplift in useful model FLOPS utilization. This translates operational improvements into measurable financial value by recovering the GPU hours typically lost to fabric and storage stalls. By aligning compute, network, optical, and storage state under a single risk-aware geometric model, data flows cleanly through the infrastructure,